third time at the festival. Gavin is a professor at University College London. Did his PhD in DMTP, and I'm an expert on all aspects of geophysical fluid dynamics, geophysical turbulence. Today, he's going to tell us about beta plane turbulence.
Okay. Thank you very much, David and Jim, for the invitation. It's a real pleasure to be here. It's like a very interesting meeting. I better start off by being completely honest. I'm in no sense a plasma physicist, and my knowledge of that area is very limited. But I do think that this problem, geophysical turbulence, well, there is some crossover with problems in turbulence and tokamaks and so forth. Hopefully will become clearer as the talk goes on, although I don't really talk explicitly about plasma physicists much. When I'm introducing this talk, I always do show a tokamak picture on the first slide and tell people that people in plasma physics are interested in the problem. I don't really say that much more about it. But okay, well, hopefully you will be the judge of how interesting this problem is to you. So, what are you interested in? Well, really, this work I've done in large part with a former PhD student, and it's about one of the sort of canonical models in geophysical turbulence, which is really the simplest model, which contains non-trivial physics of jet formation in the presence of turbulence, and it's kind of like, if you like, it's the centerpiece of, say, this book by review, which is kind of review book by Boris Galperin and Peter Reed and co-authors on zonal jets. And here's a picture of Jupiter, with that's showing some of the dynamics of the jets on Jupiter. So what do I want to say? So this first slide I'm going to come back to late in a little while, because I'm going to take a little detour and maybe discuss with you some of the ways in which people from the geophysics community kind of address these kind of problems, because there are some different kind of tools and concepts in geophysics which don't translate exactly into the plasma physics world. And I just want maybe to go through some of those to sort of show how they inform the thinking about this type of problem. But to start off with this equation, I'll just go through it quickly. Zeta here is a vorticity in a two-dimensional fluid, and then it's affected by the flow, except for this beta term, which is due to the planetary gradient in vorticity. I'll talk a bit more about that later. There's a linear friction, which is to remove energy from the system, and there's a stochastic process, which is injecting noise into the system, probably at small scales. And then this other term, which is a hyperdiffusion, which is necessary to remove entropy if we want to integrate this model numerically. One point is that you can obtain, if you know the vorticity, like as a standard, if you know the vorticity, you can get the velocity from it by inverting the Laplacian and taking the skew gradient. And the noise is white in time. This noise term eta here is white in time, has some spatial correlation function by its covariance matrix capital Pi, which will come back. So let's make a bit of a detour into some concepts which are very common and central to geophysical fluids, which might not be quite so familiar. So rather than think explicitly about the vorticity, it's more common in geophysical fluids to think about something called the potential vorticity. And in this very simple problem, the potential vorticity is just the vorticity in the previous equation added to beta y, and the beta y term just represents the gradient in planetary vorticity, because we're imagining we're on a say a periodic domain, which is like tangent plane to the planet, given by this yellow rectangle here, and the beta y is just a term which represents the variation in the planetary rotation rate in that plane. And as said, So what's important about this potential vorticity? Well, it's conserved on fluid particles. So as the fluid moves around, each fluid particle maintains the same value of Q in this inviscid unforced frictionless limit. But Q also completely determines the flow. So it's a kind of strange object in that it behaves, in some respect, in some situations, you can think of it behaving almost as a passive tracer, and I'll talk a bit about more of that later. But it's not a passive tracer because it entirely determines the velocity that's affecting it around. So you can think of it really as like an active tracer, which is kind of controlling the whole problem in this sort of idealized limit. Although in the atmosphere, in particular, large parts of the atmosphere really do behave according to inviscid unforced frictional dynamics, up to cascades and entrophies to small scales. And this is the PV for this very simple system. You can do all kinds of, there's a whole hierarchy of volts in GFD, just as there is in plasma physics. You can add in, you can look at this in shallow water equations. You get a vortex, add in a vortex stretching term, which is very much like the additional term in Hasegawa-Mima equation. You can look at it in, there's a three-dimensional analog of PV, which extends into Navier-Stokes, rotating stratified Navier-Stokes. And the concepts that I'm describing here about being conserved in fluid particles and essentially determining the flow, that issue becomes more complicated the more complicated the equations are. But these ideas carry over and inspire a whole kind of way of thinking about fluid dynamics in GFD, which is called PV thinking, which is about the next slide. So PV thinking, one sort of simple thing is you can just use the PV as like to label fluid masses. So so for example, if you think about the ozone hole in the southern hemisphere, it's actually a region of elevated potential vorticity with respect to its surroundings, and this is a sort of isosurface of elevated potential vorticity during a sort of spectacular event which happens every now and again in the stratosphere and in the southern hemisphere and the Antarctic vortex. Occasionally, something called the stratospheric sudden warming happens, where it splits into two. And this effect destroys. It destroyed the ozone hole for that winter period. The southern hemisphere, September, the end of southern hemisphere winter here. But PV is kind of useful conceptually more than that. Sorry if you cannot see this picture in the bottom. It hasn't appeared very well. But because it's an active tracer, you can actually use it to think about, to kind of explain. There was a teaching tool for like mechanisms in geophysical fluids, and this little schematic down here, if you like, shows the mechanism for the propagation of a Rossby wave, or what in plasma physics you would call a drift wave. And the idea here is that if you have a gradient of potential vorticity, so this would be a positive gradient would be positive going up, and then you displace the fluid particles there to make a wave. Well, if you raise the fluid particles, you're increasing the beta y, so you must therefore decrease the absolute vorticities or the relative vorticity zeta, and that makes an anticyclone. And then the same when you depress the contours, you make a cyclone. And if you then think about how the circulations of all of those cyclones and anticyclones then advect themselves, you can see that these, if you look at the vertical arrows, you can imagine what that's doing to the contours. You can see that it's going to cause this wave to propagate to the left. So that's like if you like a PV thinking interpretation of the mechanism drift wave. So that's really like maybe the kind of key concept that is applied in a lot of atmospheric and ocean dynamics problems to understand a lot of things that are going on. What happens in turbulent situations? Well, PV acts, it's a tracer. So if you're imagining, at least in the inertial range, if you like, things are effectively inviscid and frictionless. And PV is affected around like a tracer. And if you have a highly turbulent flow, PV is going to be mixed up. And if you mix up a tracer, you homogenize it into a single value. But if you're imagining that you're on a planet which is very large compared to the region you're looking at, and the amount of turbulence you're putting in has a kind of finite energy, well, you will not be able to mix all the way to infinity. And what happens is whenever you allow this turbulence to resolve itself, you mix instead in bands, and you get something called the potential vorticity staircase. So if you look at this plot on the right here, you can see bands, and the way to interpret this is that in each of these bands of kind of constant color, the PV has been completely homogenized, and then there's a jump to a new value of PV, which is also homogenized, and so on and so on. Hence the name staircase. So this is just an initial value problem where a ton of turbulence has been put down in the beta plane, and that the equations have been solved. This is the outcome of that process. So this process has some characteristic results because, as I said before, the potential vorticity profile completely determines the flow. So if you plug this staircase profile into the equation defining velocity in terms of vorticity and invert it, you tend to get an asymmetric jet profile where the cusps on this flow correspond. This for an idealized staircase, obviously. The cusps in this flow correspond to the jumps in the staircase, and you have smooth parabolas joining them. So the westward jets are kind of different in character to the eastward ones. The eastward ones correspond to the jumps in the staircase. So that's what happens in a kind of unforced initial value problem. All of this is really just to kind of inform some of the things I'll be talking about and try. I suppose I've introduced some jargon that we use in our area, hopefully not too much so that you can follow what's happening. So we go back to this equation then. So zeta here is the relative vorticity, so the zeta plus beta y is the potential vorticity we have been talking about. And so then these are the equations we're looking at. And you can solve this equation numerically, of course, for provided resolve this forcing scale associated with the spatial correlation in this static forcing down here. You need to resolve that. So if you run this numerically, you do indeed get jets, and this is a sort of snapshot of the potential vorticity, and it shows the banding structure, the staircase structure to some extent that I've been talking about. Although things are a little bit more complicated here, you can see waves on the, you can see distinct waves have appeared on the jumps in the staircase. And the jumps in the staircase with the PV jumps in value, you can think of as being Rossby waveguides or drift waveguides. So the idea is that it's very difficult to mix those regions because there's a very strong gradient of vorticity there. If you kick those regions, they tend to respond in a wave-like manner, whereas all of the regions in between the jumps in the PV value are easy to mix and are turbulent, and you have PV homogenization going on to a good approximation in these regions. So just in terms of understanding, so our equation is relatively simple. There turn out to be three important parameters which kind of control what the flow looks like. And they all can all be interpreted as ratios of length scales. So often the most important length scale in this problem is called the Rhines length scale. And it's usually written as u over beta square root of u over beta, where u is some characteristic velocity scale. And here the characteristic velocity scale isn't input to the problem. What's input is the energy injection rate and the friction rate, and this gives you a velocity scale. So this is the Rhines scale for the problem, and that tends to be the scale on which jets form. So dimensionally in all of these problems, you can identify the thing that the scale in which jets form. There's also something called the transition scale, which is proposed by Malcolm and Dallas some 30 years ago or so. And the idea of this is the scale in which you tend to have a transition between more isotropic two-dimensional turbulence behavior and turbulence which is dominated by beta fields, the effect of beta, and therefore forms jets. And then there's the length scale D is obviously an important length scale, and then the correlations, a length scale associated with the forcing decorrelation is another length scale. These make up the three main non-dimensional parameters. This is called the zonostrophy. Z is the zonostrophy parameter. So it's the Ryan scale over transition scale. And this really determines how zonal the flow that you get is. If this number is very large, then you get incredibly straight jets, nomenologically, like as appears on Jupiter. And if it's smaller, maybe order around 3 or 4 when you calculate it, it's got very small powers appearing here. Values of Z tend to vary over quite a small range. Not 10 practice and simulations. But so if it is up at around 10, the jets are incredibly straight. If it's around 2 or 3, you get wavy jets, such as you might see in the Earth's atmosphere. And then if it's below 1, you tend to see vortices forming in the model rather than jets. Q is quantization number. Basically, the number of jets that appear in the domain is proportional to Q. I haven't normalized it so it corresponds exactly, but the number of jets is proportional to Q. And then this forcing to jet scale, we're going to be interested in a limit where forcing scale is rather smaller than the jet scale for reasons. So we can do some asymptotics things in a little while. I said this is the kind of typical outcome that one of our simulations. Here, Z is quite large, so you're getting reasonably straight jets. Value of F is 1 is effectively small for this problem, and Q is 3 here. You get 2 jets. So you find a way of normalizing it so it gives the right number. Theoretically, then, how do we want to attack this problem? Well, one thing to do is start one way you can start off. So we say we want to go a bit beyond the staircase picture here. You can make some predictions if you assume a staircase is going to form. But in this problem we have friction acting as well. So we're not going to expect perfect tensor vortice homogenization because friction is going to be acting on the zonal flow and dragging it away from that state. So we really want to, our aim is really going to be to predict the equilibrium state U that appears as a solution to this equation if we can understand what controls the Reynolds stress term here. So our aim then is how do we find an expression for the Reynolds stress in terms of the velocity? I've written F is a functional here, so we're really expecting it to depend on the gradient of the velocity, but in general, it depends. Generally, here, just imagining it it's some function of the velocity profile. And this is kind of maybe been a holy grail of theoretical research into this problem. A closure would be really nice, especially for early climate modelers. They would have loved to have something like this. They could have plugged into models to make predictions in the days before we could integrate giant climate models and do a reasonable job with them. So there has been some progress in this area, and some of it's been quite recent. In particular, there's a very interesting paper by Jason Laurie and co-authors, which is applied what's called vortex condensation. We'll talk about it in a bit. And it was followed up by an interesting paper by Boyer and Boucher. And they come up with a very simple expression for the Reynolds stress that applies in certain situations to certain forcing profiles. And this is an incredibly simple closure, so it shows it's got a huge promise in sort of resolving, making predictions for this type of system. But the problem is that it has some singular aspects to it, which suggests it's not going to work for our jets problem, because certainly our jets have situations where the gradient in U, the latitudinal gradient in U is 0. So this is definitely going to break down. So I'll try to explain when this formula works in a little while. And you can actually plug this into, you can create you can look at actually solve for the equilibrium jet profile. If you plug in this approximation, you have a differential equation in U. You can solve it and write down the answer in terms of an inverse error function. And in some of and people like Why and Boucher have argued that this equation is a reasonable fit to the velocity profiles in between the jet cusps. But of course, when you integrate this equation, there's a constant of integration that's kind of undetermined because you don't have boundary conditions, because you know the theory breaks down the jet cusps. So you can just, all they're doing is picking D to fit their data, not that. Yep.
Just a question about the notation you're using. Is it averaged in X direction when you have?
Yeah, because of the symmetry of the problem, the ensemble average effectively averages in the X direction. So almost any kind of average has the same effect. And it's like averaging over the stochastic forcing does the same job. Then there's another very interesting paper in the Journal of Atmospheric Science by Srinivas and Young. And they come up with a nice formula for the momentum flux, which applies to all forcing profiles and frictions. They kind of emphasize a really odd result, which is if you make the forcing isotropic, the momentum flux is 0. And that's kind of odd because when people set up numerical experiments, they've often forced them with what they consider to be an isotropic forcing in wave number space. They often what you do is you make an annulus in wave number space and force at the wave numbers that exist in the annulus. And they call that isotropic forcing, and they do not see the momentum flux that they get is 0. So there's a kind of puzzle here. I should say that Srinivas and Young are going to be the heroes of this talk. So this result turns out to be an anomaly, and it actually turns out to be a cautionary tale of working in an infinite domain. You really want results for a finite domain.
Can you justify physically this idea of isotropic forcing? I cannot.
I'll tell you what's done in the numerical model. Yeah. So physically, I mean, the idea is that you have an infinite beta plane, and you just take the Fourier transform of your I mean, I think you're actually. I think maybe you're intuiting the point that I'm going to make, which is that in a real domain that you can't have this. Yeah. Right. Okay. So where was I? Oh yeah. So then, this list of kind of puzzles I've just been talking about. Can we resolve these curious results? And do numerical simulations with isotropic in inverted commas forcing gives non-zero momentum flux. Does this contradict their result? And what happens at jet cusps? And how does the beta effect into the problem? Yes, so I suppose that in terms of our problem, this result is kind of catastrophic because it doesn't contain beta, and yet we know that jets appear on the Rhine scale, and the Rhine scale does involve beta. So this is just definitely not going to work in helping us to understand the problem. But I'm going to show her. But the interesting thing is that this idea does work in a very closely related problem. So let's look at that for soon. Yeah. So this is the Laurie et al. Paper I mentioned earlier, and this is a very nice result, for a very closely related problem. The idea here is that there there's no beta in this problem. In fact, there's something the exact same equations I've written down with beta equals 0, and they're running them out to some sort of statistical equilibrium. And these things they call vortex compensates, and these things just translate into their domain for all time with a reasonably constant. Yeah.
I have some doubt about this. This isn't regular, of course.
Yes, yes.
Yeah.
So,
No, but I can tell you the filamentation. I mean, we have done that a lot. This kind of final state. Well, the forcing is maintained.
yeah, the forcing this
Okay.
this out to statistical equilibrium.
It is
Statistical
with-
equilibrium. Yeah. This is
All this randomization is, but normally you have a bad filamentation, which is very clear to see, but here
yeah.
filamentation
This
is all based on
this is a statistical equilibrium in a force dissipative
Yeah,
system.
okay.
And
But that's the forcing which creates this kind of effect.
yeah, sure.
I
Sure. Well, anyway, let's explain what success they had, and that is what so essentially they applied the circular geometry version of this result that for a large class forcings in the limit of small friction, momentum flux is given by the energy injector rate over the local shear in the velocity. This is the spherical geometry version of it. It also gives you a differential equation in U that you can solve, and the solution to that equation is that U of R is a constant in the core of these vortices, and it also gives you the value of that constant, which is and this plot is given by this dotted line, and here are their numerical results for the two vortices in Mahler. And showing that the theory does a pretty good job in this particular force distribution problem. So anyway, so the key question that I was really fascinated by, and that I get kind of collaborated with my student William Jackson on for, of course, his PhD, is why does this seem to work here, and doesn't give us anything helpful or anything useful in the case of the beta plane turbulence problem, which I've been talking about. Right. Following approach, which is kind of widespread in non-equilibrium statistical mechanics approaches to this type of problem, instead of considering the full nonlinear problem, what you can do instead is neglect wave-wave interactions in the perturbation terms in the equation. And the idea here is that the eddies are the eddy-eddy interactions are kind of dominated by mean flow, and all interactions or perturbations to the zonal mean with themselves can kind of be neglected in this problem because the mean flow is so dominant in the equilibrium state. You can construct a set of equations called the quasi-linear equations, where you simply just neglect those eddy-eddy interactions. And then you can also consider a set of equations for the statistics of this system, which is called, in the literature, it's called CE2 for cumulative expansion of second order. And you construct this quantity Z, which is a function of the coordinates in the system doubled. And it's like the correlation between zeta prime at one point and zeta prime at another point in a system. And you can construct a big set of equations for Z from those. I'll spare you the details. The ones and the twos here refer to which coordinate we're differentiating with respect to in this expression. So the disadvantage of this is you've doubled the number of dimensions of the problem. You're now working in the domain squared, which is kind of difficult if you want to solve these equations directly. It is possible when you have some symmetries. Pi is the correlation matrix. So this equation is forced by pi, which is the correlation matrix or a covariance matrix for the forcing we put in at the beginning. And if you know Z, you can do a calculation where you get the momentum flux. That's an important detail. So just to give you some confidence that it's if we solve the quasi-linear equations, and we solve the period expansion equations, which we can do directly by numerical integration in this problem, and we solve the nonlinear problem, we get something broadly similar in each case. We don't get exact agreement because we expect exact agreement asymptotically only in the limit z equal 10, z is large, and here z is about 5 in these simulations, I believe. So there's some differences between the jets in nonlinear simulations compared to the quasi-linear ones. But let's start by trying to make predictions about the quasi-linear system and see if that can help us in the nonlinear system. Yeah.
Nonlinear simulations, they agree with each other?
No, the quasi-linear equates with CE2 pretty much exactly. CE2 is describing the statistics of the quasi-linear system. So for CE2, I'm actually solving this equation for Z. Yeah.
It's just, do you expect agreement
You
between two nonlinear simulations that you run with different
in this system qualitatively you get good agreement. Yeah, the equilibrium states are pretty robust, and I suppose that if you have a very large domain, you might have and depending on the value of Z, you can have situations where jets split and merge and form to infinity. But if Z, the larger Z is, the more steady the state is. So as I said, Srinivasan and Young are kind of the heroes of the talk. So I'm going to say a little bit about what their contribution is, because they kind of solved the problem of the momentum flux associated with the small scale forcing exactly. And how do they do that? Well, they don't try and solve the equation for this correlation function Z explicitly. Instead, they look at a simplified case, and they're thinking in particular of what our parameter f being much less than 1. That corresponds to the scales of the eddies we're putting in being much smaller than the scales associated with the jets. And that means that each individual little eddy that's being forced, if you like, sees only a linear shear in its vicinity. And that motivated Srinivasan and Young solve this equation where U is replaced by a linear shear, which we're calling gamma y bar. Y bar here is the difference between one y coordinate and the other in this system, and because we're exploiting isotropy essentially to reduce the number of dimensions. Z bar is the difference in the z coordinates. And then this is a first order ODE in Z. The way that they solve it is they transform to Fourier space, where you also have a first order. Then you have there you have an ODE which you can integrate, and then you can express the Fourier transform of Z as a function in terms of a kind of an integral involving the Fourier transform of the forcing function. I hope that's clear. But the point is, for this simplified case where the flow is a linear shear, you can actually solve the CE2 equation explicitly, and we have a formula on the other slide for getting the momentum flux in terms of Z, and this is the momentum flux in terms of the Fourier transform of Z in a handy form for calculations. So this is kind of nice. It's like we're solving everything in a sense, or it feels like that. So one of the things my student William Jackman did, which was nice, is the formula that appears in the appendix of Srinivasan and Young is kind of horrible. And we also have written down the formula, which is somewhat horrible, but I feel it's nicer than theirs. And this is our formula of the momentum flux. And so what it turns out is the momentum flux is always proportional to the energy injection rate divided by the shear rate. And then it involves an integral over an angle of this thing, which is a density function P multiplied by a kernel function K. So how do we interpret this? Well, the interpretation is the momentum flux associated with an eddy depends only on the angle of the wave number vector that you're forcing at, and this parameter, which is friction divided by shear. So I said P is a density here, so this is really just it's just really the ratio of the angles of the wave number forcing that you're forcing at, like a density in wave number angle space, and this thing always integrates to 1. So because the magnitude is being scaled out to P factor. And then everything hides in the kernel function, which has an explicit analytic form here, which is kind of complicated. It involves the exponential integral with complex argument. That's not important, just the fact that it works. So the question is then, does this formula help us to understand all the things that I've been talking about, seeming paradoxes? Well, it helps us understand Srinivasan and Young's crazy seeming result, because it turns out to be an analytic fact that if you integrate the kernel function from minus pi to pi, you get 0 always, and that means that if you have a uniform distribution in wave number angle, this thing always integrates to 0. So that shows Srinivasan and Young's result is correct if you believe in isotropic forcing, but of course I'm about to explain why that doesn't work. Well, it's a curiosity, or it's a cautionary tale about working in an infinite domain when you really want results for a finite domain. But you can also see the other result, the kind of headline result. Let me go back a few pages to the headline result, which was all Laurie's result and everything was based on, is that the momentum flux is given by the energy injection rate divided by the shear rate. Well, that turns out to be true. You can see that also works because in the limit of small friction, which corresponds to the limit of alpha going to 0 in the kernel function goes to 1 for all angles if you take this limit in between minus pi and pi, which kind of seems weird. How can these both be true? Well, it turns out that at angles just less than pi, as you take the limit of small friction to 0, you get a kind of singularity appearing there. And so this and the point that you kind of brilliantly intuited or knew already is that in a finite domain, when you start to take this limit, you won't have any wave numbers in the region which is contributing to this singularity. So therefore, the Srinivasan-Young result for isotropic forcing is a mathematical curiosity which should be discarded. But it's still true. Mathematical. So the point is we can see that the Boucher result or the Laurier et al. Result, the Laurier et al. Result where the momentum flux is given by the energy injection rate over the shear, that result seems to apply, and it will apply to a wide range of, well, any forcing that isn't isotropic, essentially, provided you make the friction small enough. So let's try and explain. How am I doing for time? Actually,
You're fine.
Okay, right. Okay. So what's going on? Well, the way to think about this is to think, or to understand a little bit about what's going on is, you think about how momentum fluxes actually depend on the angle of the wave number you're injecting. So if you inject waves with a large negative tilt here, they get affected by the shear flow until their wavefronts become vertical, and then they get they're affected over until they've got large positive shear. And if the friction is very small, you'll have momentum fluxes which are negative in this region, and then you'll have and the contribution for those will be cancelled by a momentum flux from this region, which will be positive because the momentum flux depends on the phase tilt of the wave. And it turns out that when you do the maths, the contribution in the small friction limit, the contribution for any tilt turns out to be the same when you integrate this forward in time, taking account that the wave is decaying a bit under the friction as it goes. The exception is the waves which have an incredibly narrow negative tilt, which contribute an enormous negative momentum flux, because if they're tilted far enough, they'll take almost an infinite length of time to reach the state, by which time they'll be dissipated. So they'll be dissipated entirely while they've got negative tilts, and they'll contribute a large negative momentum flux. But in a finite domain, those waves simply won't exist. Friction is small enough, so you'll have a contribute. You'll actually be living in a situation where all the waves contribute the same amount of momentum flux, according to the Wye and Boucher results. So we thought we understood something about the system after this, and we decided to go back to our simulations, and we decided to replace our stochastic forcing in the simulations with a forcing which is purely in the zonal direction, based on the momentum flux calculated from the Srinivasan and Young result. And what we get when we run the model forward is a pretty good. Sorry, people can't see the jets. It's supposed to be able to see jets on the side there. Maybe you can see them on the screen over on the right. You get a really nice agreement between the nonlinear simulations and the parameterized simulations. So we've totally removed all stochastic forcing from this deterministic parameterized simulation. But what we didn't do is remove the non-zonal contributions completely, because a crucial ingredient of this simulation is to allow secondary instabilities to develop in the flow as it evolves. And so really, what we're saying here is the Srinivasan Young parameterization can do a great job of creating a simulation where effectively the same jets appear, provided you allow the flow to develop secondary instabilities. And if you look closely at this picture, you can see, if you look at the waves on some of the potential vorticity jumps, you can see waves with a kind of characteristic wavelength here, say, fairly similar between the nonlinear simulation and the parameterized simulation. And you can see longer waves down here on these jumps in potential vorticity, which also maybe you can't see, but also appear to some extent in the stochastically forced case. And these started to be characteristic of two different instabilities, one which is due to the westward jet and one which is due to the eastward jet. And those two instabilities seem to be independent. The flow seems to be in a state which is marginally unstable or close to marginally unstable. Two different instabilities, one related to each jet, and those are rather different in character because theta puts a direction into the problem. So you've got a different type of the instability which emerges at the westward jet is different in character to the one that emerges at the eastward jet. Here's a nice picture which might be easier to see some of these things. You can see clearly waves that waves have appeared on this jumping vorticities. I think the waves are a little bit longer than the shamanistic simulations, but we're replacing all stochastic forcing, so we are making simplification. How long do I have, you say? Okay. Right. So I've made some claims about secondary instability. So William Jackman, my PhD student, spent some of his thesis investigating these. So I'm going to show some results about that. And also we also did some things to kind of test the Srinivasan-Young theory a bit more carefully. One thing we did to start with is we just drew down a flow, which I think is pretty similar. I don't think there's no picture of it here. We threw down a flow, which I think is, yeah, it's just a sine wave, and then we calculated the Srinivasan-Young prediction for the momentum fluxes, and then we varied F because, as I said, the Srinivasan-Young theory is a small f theory, F being the ratio of the scale of the forcing to the scale of the jet. And we looked at the convergence of the Srinivasan-Young predictions to the actual fully calculated momentum fluxes, and we saw that if F is F's taken down to 7 times 10 to the minus 3, we have F varies between 7 times 10 to the minus 3 and 0.1 in the simulations, and here it is sort of if you zoom into the cusps of the jet, that's where the agreement is the convergence is slowest, but we do converge somewhat gradually to the exact Srinivasan-Young result. Momentum fluxes converge exactly. So this is really one of the first things we did, actually, show that we're on the right lines that we could predict. The Srinivasan-Young theory could predict the momentum fluxes, at least in this limit of small f. Then we did a calculation which kind of was to prove that secondary instabilities are essential, which is we did a calculation in the this is just in the quasi-linear situation, although we achieve something similar in the nonlinear one, I think. If we made the parameterization purely zonal, we suppressed all possibility of secondary instabilities, we get something which is catastrophically different. Jets are on the wrong scale. In fact, beta doesn't enter this problem. These jets are just limited by friction. The secondary instability is the only way in which the jets kind of know about beta problem. So the parameterization, the parameterization of forcing isn't the full story. It's really just showing you the stochastic process is having the same effect as a dynamical forcing, which is then forcing the flow into an unstable state, and then the secondary instabilities are doing a job. Then have a role in determining the equilibrium state. So that the take-home message of this side: secondary instabilities play a key role in the equilibration of the flow. I don't know much to talk about this. So you could make a linear instability analysis of the flow. So there's actually a nice PV thinking in kind of explanation of how flows of this type lead to instability. The key message is you have to have a change in the potential vorticity gradient occurring somewhere in the flow in order to have instability. That's called the Rayleigh-Q criterion. In geophysics, this eigenvalue problem we're solving is called the Rayleigh-Q eigenvalue problem. Of course, we're looking for unstable modes for instability. And to have unstable modes, you need a change in sign of the potential vorticity profile, which is related to PV. If you have PV homogenization, which I was talking about the staircases, PV gradient vanishes. So if you have homogenization, you're close to satisfying the Q criterion. What actually happens in our simulations? Well, the PV gradient is given by this red line, and 0 is here. You can see at both the eastward and westward jet, PV gradient gets very close to 0. So it suggests that both the eastward and westward jets are very close to a state of marginal stability, because the condition necessary for instability, the Q criterion, requires this PV gradient to change sign. The character is completely different because at the eastward jet, you've got a very strong PV gradient because that's where the step in the PV profile of the staircase is, corresponds to this jump here. And the PV gradient is close to 0 in the jet flanks. But at the westward jet, the PV gradient is close to 0 at the jet core. And so you've got kind of different dynamics occurring at the eastward jet and westward jet. This is the result of our stability analysis. So this plot is a functional plot of growth rate against wave number on the x-axis. And in constructing this plot, we're kind of conscious that if you just do a stability analysis of the time mean flow, well, that might not tell you diagnostically as much as you want to know, because you could be, if you're marginally unstable, you could be close to a powerful instability. At least flow in practice, flow is fluctuating around a little bit. And so what we did is we varied beta to kind of show that there's an if you make small changes to the equations, it could have varied U to get the same effect. That there's an unstable mode which is kind of lying just below the surface of when you do stability analysis for the time mean flow in the problem. And that you see, in fact, that there are two such modes, one with around wave number 6, which lives on the eastward jet, and one with about wave number 3, which lives on the westward jet. And hopefully, you might agree that when you look back at the numerical in simulations back here, or at least in this case, you can see this wave number 6 on the eastward jet. On some extent, maybe you can see wave number 3 or 2 or 3 patterns appearing on the westward jet in the dark region. Maybe the picture isn't clear enough. And we've also done a lot of kind of calculations looking at the momentum balance in the equilibrated state, and you can see then the contributions from the momentum fluxes due to the secondary modes associated with these secondary instabilities. They play a role, as does the direct momentum flux from the small scale forcing. And so the balance is kind of this complicated mix of momentum fluxes from the friction, on the one hand, momentum fluxes directly from the small scale forcing, which we can parameterize, and momentum fluxes from the secondary instability, which we can only really calculate using the linear stability analysis. And there are various pictures here which kind of looking at the momentum balance due to modes in the quasi-linear and non-linear runs. The non-linear runs a bit messier because we're not at very high Z, we get lots of waves scattering to different wave numbers, but you can still see signature of shorter waves at the eastward jet and longer waves at the westward jet, and the momentum fluxes add up in a way which we kind of expect. So I kind of outlined some puzzles earlier in the talk. I'll just go through these to sort of summarize. Can the Srinivasan, Young, and Boyer-Boucher results both be correct for momentum fluxes? Well, I would say yes, but true isotropic forcing is unrealizable. So a cautionary tale when you're using infinite domains, you've got to be careful. Numerical simulations, the isotropic forcing give non-zero momentum fluxes. Does this contradict Srinivasan, Young? No, the forcing isn't truly isotropic. F is finite, secondary instabilities are present. What happens at jet cusps? That's why Srinivasan, Young still does a good job at small f, and secondary instabilities are key at the momentum balance at the jet cusps is dominated by momentum fluxes from secondary instability modes. And how does the beta effect into the problem? Well, as I said, through secondary instabilities at both the westward and eastward jets. So maybe actually, maybe should have said, I suppose at the beginning I had an equation where I wanted to write the momentum flux as a function of the velocity. Can you describe it? Can it ever be described as a purely zonal closure theory? Well, not really, because these are the modes that emerge are kind of global. They're global in scale, but they're on the scale of jets to some extent. So it's not. You certainly can't have a local theory, which that's not going. A local theory is not going to tell you what the momentum fluxes are to these secondary instabilities are. I said parameterization is possible in a non-zonal setting. So you can say that our parameterization could be useful in a situation in simulations where you have a small scale forcing. Even in this type of problem, the scale of the secondary instabilities is much larger, can be much larger than the scale of the small scale forcing you're putting in. So our parameterization ideas have got potential for large computational savings, so long as you work out what the relevant secondary instabilities are going to be and resolve those. There could still be a big scale separation between those and the forcing. So I'll stop there and have questions, I think.